We've made it to chapter 3. Chapter 1 was like, hey, this is an integral. Here's how you do some integrals. Chapter 2 was, hey, here's all these things that we can do with integrals. And chapter 3 is, well, how do you actually do them? So in chapter 2, a lot of the times it was like the dad telling the kids, well, I'll tell you when you're older. We get an integral. We don't know what to do with it. I'll tell you when you're older. You guys are older now and you get to learn all the truths, all the ugly truths about real life, or at least real calculus, or at least calculus by hand. Really, the ugly truths about calculus are all the numerical and computational stuff that we're not going to talk about. Anyway, so you're old, but you're not that old. So again, like we're going to introduce a lot of stuff in this chapter. So an integral, maybe like, this is going to be our first integral of the day, x e to the x. We can't do this right now because we don't have any sort of product rule or integration for antiderivatives. And a u substitution won't work here. If it were e to the x squared, a u substitution would work, but we don't. Later on in the chapter, not today, we'll do something like this. And if you're really creative, you actually might be able to do this second integral right now, but we'll generalize. How do we deal with integrals with a bunch of trig in them? Turns out the answer is just a lot of trig identities. So it's not really any new calculus in that section, but yep, trig is coming soon. And then the third section in chapter 3 is huge because I can't tell you how many times we've seen something like this. And I just say, well, you can't do it yet. Can't do it yet. Sorry. And this is kind of like a reverse u substitution. It's called a trig substitution. And instead of letting u be equal to something, we let x be equal to something and then use trig identities. Fun fact, this integral involves secants and natural logs. You wouldn't expect it, but it does. Anyway, what else are we doing? Oh, yeah. And then we got partial fraction decompositions. It'll be like, what happens if we want to do some sort of integral like this? Again, a u substitution would not work in this case. And again, this is actually not calculus. We don't use calculus methods really to solve this. It's really all just really weird fraction stuff. Division of fractions and... it's called partial fraction decomposition. Really kind of wacky. And then we'll end this chapter with improper integrals. Let's not go from 0 in this case. Something like this. So now this last function is kind of interesting because it's 1 over x squared. It looks like this. So again, it's maybe surprising that we could integrate off to infinity. And this area is just equal to 1 or 1/2 or 2 or something like that. I don't remember the number, but it's no bigger than 2, which is kind of crazy. But if we integrate 1 over x, which looks very similar, the integral is actually infinity. So we'll talk about that in the end of the chapter. And that's kind of what we have coming up, okay? So just lots of integrals, but don't worry. If you're missing chapter 2, we'll sprinkle some of that stuff in there. In fact, in today's 4th video, we'll talk about definite integrals, and we got some chapter 2 stuff coming back. So don't worry about forgetting it. We'll be always refreshing your mind. And that's kind of what we're doing. So let's start by talking about integration by parts. This is maybe the most powerful. Well, u substitution's the most powerful, maybe. Maybe second most powerful. It's very powerful technique for integration. So let's go back to the product rule for derivatives. And that said that if I want to take the derivative of 2 functions multiplied together, this is a shorthand we can use for that. We can't just take the derivatives individually. That's similar to the fact that we can't just take the antiderivatives individually. So in the product rule, we said, well, this is f prime g plus fg prime. Integration by parts is basically just the product rule, but not as nice. All right, that's Calc 2 in a nutshell. Undoing Calc 1, but it's usually not as nice. So let's integrate both sides. We can think of integrals as the area under the curve. We can think of integrals as antiderivatives. There's a lot of ways that we can think of integrals. But what's true is that if two functions are equal to each other, their antiderivatives will be equal to each other up to a constant. Okay, so if we integrate both sides, what do we get? Well, the antiderivative of the left-hand side is easy. It's just f times g. What's the antiderivative of a derivative? It's just itself, again, plus some constant. We're going to leave off the plus c's for now, just for this formula, and we'll see why that kind of works at the end. But for now, just take it on faith. And then this will be the integral of f prime g plus the integral of fg prime. And now what we do to get the product rule is just get this guy by itself. So the integral of fg prime is equal to this minus that. And that's integration by parts. This is our new formula. It probably doesn't look that interesting. It probably doesn't look that strong. It doesn't look that effective. Jason, you're telling me that this formula has another integral in it? How is that helpful? But it is. I'll show you why it is. Okay, so let's clean this up. So this is basically integration by parts. It's a formula that we can use to evaluate integrals. I said it's really powerful. It doesn't look that powerful, but strength can sometimes be deceptive. Looks can be deceptive, I mean, whatever. So usually what we do is we let u be f and v be g, and then f prime becomes du, and g prime becomes dv. All right. Because really what we have is g prime is g of x dx. Like this is shorthand, but technically this is g of x dx. So it does work out. And then we get the integration by parts formula that the integral of u dv equals uv minus the integral of v du. And this is integration by parts. I should have mentioned it at the beginning of the section. I forgot. I'm never writing integration by parts ever again. Okay, IBP. A lot of people and textbooks just say by parts, but that's too many well, same, it's actually fewer syllables. It's too many letters. IBP is what I'm going to always write. Integration by parts. I'll still say integration by parts. So this is our formula. We're going to see it in action. It's basically just the product rule, moving things around. And again, take it on faith that this is actually useful, because it doesn't look useful. All right. It just looks like you're making a bigger mess. And sometimes it looks like you're making a bigger mess. But just like when you clean your house when it's really dirty, sometimes it like looks worse before it looks better. And sometimes that'll happen for integration by parts too. So let me give you a little baby example, show some motivation for how this might work. And then we'll get into some more of the intricacies of this method. Example 1. Evaluate integral of x e to the x dx. I told you we'd be coming back here. If we let u be equal to x, and now note the position I'm writing this. That's very intentional. dv is e to the x dx. So leave room here and here, because there's two things that we need there. So again, if this is u and this is dv, again, we have our formula that the integral of u dv is uv minus the integral of v du. Voodoo, if you will. One of the ways to remember it. I don't know what this is. Uv. Uv minus voodoo. I got nothing. Okay, so how can we evaluate this? Well, it's just u, which is x, times v, which, oh, we don't have v yet. But we can find it. right? What was dv? dv was just the derivative of some function. So v is just the antiderivative. What's the antiderivative of e to the x dx? Antiderivative of e to the x is itself. And I'm going to write a plus c in green because it's true. The antiderivative of e to the x dx is e to the x plus c. As a side note, the reason why we don't have a plus c in this formula is because we already have an integral right here. So the plus c will come from this one. Because it doesn't matter if we have plus a constant plus a different constant. That's still plus some third constant. That's a combination of the first two constants. So we only need one constant in those cases. So v, right, is, we said that's e to the x plus c. I'm going to write all the plus c's in green. You don't have to change colors. Minus the integral of v, which is, again, e to the x plus c. du. Oh, we don't have a du. Okay. We need to find du. So du dx is just 1. So du is just 1 dx. It's always just going to be the derivative times dx here. That's how you get to du. So again, the way that we've set this up over here is this is just what happens when you take the derivative. And this is what happens when you take the antiderivative. So it's again v du. What's our du? Oh, it's just dx here. Oh, well, look what we have. We started with something that we could not antidifferentiate. And now, well, this is just something that's done. And this we can take the antiderivative of. Ah, it was helpful. We'll talk more about why it was helpful, how to recognize it, and stuff like that in the next video. But for now, just see and notice, oh, we can do this now. Neat. So what we get is x times e to the x plus x times c, or we can call it cx. We usually write the constant first. Okay, minus this antiderivative. Well, the antiderivative of e to the x is e to the x, and then we have the plus cx, and then we have another plus c. Oh, we should call them different c's. Call this, I don't know, c2. So here's why this green doesn't matter, and why we're never going to write what's in green ever again. Every time you do integration by parts, this is going to happen. We're going to have a plus cx. Well, it might not be an x, but it'll be a plus c times something and a minus c times something. So this green thing over here will always go away. We're never going to write it ever again. But technically it's there. It just will cancel out every time. So we just save a little bit of work. And then usually we just call this plus c. October, you're not scratching my chair, are you? He was. So what do we get as our final answer? October. You better be doing our calc homework after this. We get x e to the x, and then minus e to the x, and then minus c2. We're just going to call that, I don't know, some other constant, where negative c2 equals c3. That's our antiderivative. Some people will factor out the e to the x, but you don't have to. Every time, let's remember chapter 1. We're taking an antiderivative, we better check our answers. And that checking of the answers shows this connection to the product rule. What if I take the derivative of this? Take the derivative of our answer, we have to use the product rule. The derivative of the first function times the second, plus the first times the derivative of the second, and then minus the derivative of e to the x. These cancel, and we get x e to the x, which is exactly what we wanted. Antiderivative and derivative should cancel each other out. And again, there's that constant when we take the antiderivative. So that's how integration by parts works. It's related to the product rule. And a lot of times we get something like this where we differentiate with the product rule, one of the terms cancels out with this other guy, and the other term becomes what we wanted. That's what integration by parts is all about. I'll explain this a lot more in the next video, but I wanted to just introduce it in this one. Let me know if you have any questions, and good luck.